Section 6.4 is areas of surfaces of revolution. And whenever we revolve a curve around a fixed axis, we generate just the surface area. This is similar to what we did in section 6.1 and 6.2, where we revolved a rectangle or a shaded region around an axis. We generated a solid shape. Now all I want to do is find the surface area of that solid shape. So how we do that is we revolve a curve around a fixed axis. And when we do that, we can divide this curve into these strips. It'll generate a cylindrical surface that looks like this. If we revolve just a line segment around an axis, we generate this strip. If I were to cut this strip along this line right here, I could flatten out that cylindrical shape and I would have a rectangular shape. The circumference of that cylindrical shape ends up being the length of this rectangular shape, and how we get that is we look at 2 pi r. The circumference of a circle is 2 pi r. The r here is the radius. It would be the distance from the axis of revolution to the outside edge. So if I'm revolving around the x-axis, the radius would be y. So we would say the length of this rectangular strip is 2 pi y, and the width or the thickness would be our delta x, whatever we wanted that to be. So then I could add up all of the lengths of these strips from A to B, and then I would have my surface area. So what we could say is that the circumference or the surface area of this circle would be the sum of 2 pi r times the arc length. And the arc length is what we just finished going over. So to get the surface area, we would look at 2 pi times the integral from A to B of our radius, which is the distance from the axis of revolution to the outside edge of the curve, times the arc length, which is the square root of 1 plus the derivative squared dx if we're integrating with respect to x. The radius here would be y. Can you envision how this works? This formula needs to be committed to memory as well. So we revolve only the bounding curve to generate a surface area, not the solid shape. And I kind of talked you through how we would develop this, so I'm going to move into an example problem. We know that we're going to need the derivative and be able to square it. So we start by finding the derivative. And since this is scratch work, I'm going to find the derivative in green. So that we've got y equals 2x minus x squared raised to the 1/2 power. We want to find the area of the surface generated by revolving this curve about the x-axis. Since they gave us y as a function of x, our radius here is going to be y because we're revolving it around the x-axis. So y prime is going to be equal to, we have to use the chain rule to find the derivative. So that's going to give us 1/2 times 2x minus x squared, subtract 1 from 1/2, and that gives us a negative 1/2. And then we multiply by the derivative of what we took the square root of, and that's going to give us 2 minus 2x. Cleaning this up, we're going to end up with, I could factor a 2 out of here, and so that 2 would cancel with this 2, and on top that would leave me 1 minus x over the square root of 2x minus x squared. That radical's in the denominator because of the negative exponent. Are we okay with this? Now we need the square of this derivative. So that means I'm going to square the numerator and square the denominator. So this gets plugged into, I'll write down the formula again. The surface area is going to be 2 pi times the integral from A to B of our radius, which in this case is going to be y, square root of 1 plus y prime squared dx. So we get that our surface area is going to be 2 pi times the integral from where to where. How do we get the bounds for this? It's given, it's the bounds on x because I'm integrating with respect to x. So that's going to be 0.75 to 1.5. Y we said was this function, the square root of 2x minus x squared, and then we have the square root of 1 plus 1 minus x squared over 2x minus x squared dx. So to simplify this, the first thing that I'm going to need to do is combine these two terms and see if I have anything that'll come out from under the radical, which means I need to get a common denominator. So to get my common denominator, I'm going to take the 1, so that is going to give me 1 plus 1 minus x squared, 1 minus x quantity squared over 2x minus x squared. To get a common denominator, I'm going to multiply that 1 by 2x minus x squared over 2x minus x squared. And I should probably also FOIL this out. So when I do that, that's going to give me 2x minus x squared. And when I FOIL this out, I'm going to get 1 minus 2x plus x squared all over 2x minus x squared. When we combine like terms, we see that the 2x's are going to cancel out. The x squares are also going to cancel out, and we just get 1 over 2x minus x squared. So this is what I'm going to plug in place of this expression right here. Do y'all see that? So that was all the scratch work for how to simplify that radicand on the integral. Moving down here now, we're going to say that this is going to give us 2 pi times the integral from 0.75 to 1.5 of the square root of 2x minus x squared times the square root of 1 over 2x minus x squared dx. Well, we can distribute this radical across the numerator and the denominator, and then these two radicals are going to cancel out. Do y'all see that? The question was, where did the plus 1 go? The plus 1, when I combined these two terms right here in the scratch work, I multiplied that 1 by 2x minus x squared over 2x minus x squared in order to get a common denominator, so that I could just combine the numerators over that common denominator. When you ask where did the 1 go, this piece right here was from the 1 right here, and then this is what I got when I FOILed out this. So then when I combine like terms here, the 2x's are going to cancel out, the x squares are going to cancel out, and I'm just left with 1 over 2x minus x squared. So that got plugged in for the entire expression underneath this radical. That's where that came from. So now I have this expression on top, same expression on bottom. They're going to cancel out, and that's going to leave us with 2 pi times the integral from 0.75 to 1.5 of 1 dx. And what do you get when you integrate 1 with respect to x? X from 0.75 to 1.5. So using the fundamental theorem of calculus, then, we're going to plug in our upper bound and get 1.5 minus plug in your lower bound, that's 0.75. And 1.5 minus 0.75 is 0.75, but 0.75 you can write as 3/4. And then that 2 will cancel with that 4, and we're left with 3 pi over 2. So most of the work here was done in the scratch work where I found the derivative squared and where I combined these two terms underneath the radical to simplify the radicand. And I wanted to do that so that I could simplify the integrand, which makes the integration way easy. And then evaluating the integral is not terribly difficult either. So in example 2, we're asked to find the area of the surface of revolution for the following curve. And I give you a picture. It's not necessary to draw the picture for these all the time, but it does help occasionally. So just to remind you, the integral for surface area is going to be 2 pi times the integral from A to B of your radius times the arc length. And then this, because our bounds are given along the y-axis here, I'm going to integrate this with respect to y. I know that because of the bounds that I was given. Those will then become the bounds on the integral. Well, I'm revolving this around the y-axis. So remember, your radius is going to be the distance from the axis of revolution to the outside edge. Well, that distance, when I revolve around the y-axis, is going to be a distance of x. So my radius for this problem is going to be x. And then to get the arc length, I'm going to look at the square root of 1 plus x prime squared dy. So that means that I've got some scratch work to do. I need to find the derivative of x squared. So we're given the function x equals, and I'm going to write it like this. It's 2y minus 1 raised to the 1/2 power. So x prime is going to be equal to 1/2 times 2y minus 1, subtract 1 from the exponent, and you get a negative 1/2. And then multiply by the derivative of what's on the inside, and that's just going to be 2. So the 2 and the 1/2 are going to cancel each other out. So I end up with x prime is equal to 1 over the square root of 2y minus 1. My next step then would be to square this, and I'm going to move it up here for more room. So x prime squared ends up being 1 over 2y minus 1. This is what I'm going to plug in here in the integral that I set up. So I think now we're ready to set this problem up. So we've got, for our surface area, 2 pi times the integral from 5/8 to 1 of the radius, which we said was x, but what was x equal to? It was equal to the square root of 2y minus 1 times the arc length, which is the square root of 1 plus 1 over 2y minus 1 dy. So the next thing you want to do is you want to combine these terms, and that's where I'm going to do this right here as scratch work. So to combine these terms, I have 1 plus 1 over 2y minus 1. I need to get a common denominator, which means I need to multiply this 1 by 2y minus 1 over 2y minus 1. And when I do that, that gives me 2y minus 1 plus 1 over 2y minus 1. The ones on top are going to cancel each other out, and we're just left with 2y over 2y minus 1. So this is what I'm going to plug into my integral right here to clean up the integrand. So that's going to give us 2 pi times the integral from 5/8 to 1 of the square root of 2y minus 1 times the square root of 2y over 2y minus 1 dy. So this radical will cancel with the denominator there. We get 2 pi times the integral from 5/8 to 1 of the square root of 2y. Well, that's just the square root of 2 times the square root of y, which I can write as y to the 1/2 dy. Now the square root of 2 is a constant, and I can pull that constant out of the integral, can't I? That's going to give us 2 square roots of 2 pi times the integral from 5/8 to 1 of just y to the 1/2 dy. And when we integrate that, we get 2 square roots of 2 pi times, we add 1 to the exponent, making that y to the 3/2, and divide by 3/2 is the same thing as multiplying by 2/3, and then we get 5/8 to 1. So we're going to plug in our upper bound. Actually, I'm going to pull the 2/3 out, and that's going to give us 4 square roots of 2 over 3 pi for our constant. And then we're going to plug in our upper bound, which is 1 to the 3/2, minus plug in your lower bound, that's 5/8 to the 3/2, and we could leave that as our final answer. There's a lot more scratch work involved than actual calculus work, just trying to set up the problem so that we can do the calculus with it. You do want to show your scratch work for most of this. Example 3. Here we're told we're given y as a function of x. Our bounds are along the x-axis. We're revolving around the y-axis. So here's the curve. I went ahead and graphed it. We're going to revolve this shape around the y-axis. So when I do that, my radius is going to have a distance of x. That's going to be my radius. So when I set up my integral, I use 2 pi times the integral from a to b of my radius times the arc length. Now the bounds that they gave us were along the x-axis, so do I want this to be a dy or a dx here? Dx. If they give us the bounds on the x-axis, I want this to be a dx, okay? So we said that our radius is going to be x, and I'm given y as a function of x. Well, that makes the dx make sense, right? So my arc length is going to be the square root of 1 plus y prime squared, and this is going to be a dx. So I'm going to come over here and do some scratch work. I'm given y equals 1/3 times x squared plus 2 raised to the 3/2 power. Now I need to find the derivative. Well, that's going to be 1/3 times 3/2 times x squared plus 2 raised to the 3/2 minus 1 is 1/2 times the derivative of what was inside the parentheses, and that's going to be 2x. Now I want to clean this up. This 2 will cancel with this 2, this 3 cancels with this 3, and we're left with y prime equals x square roots of x squared plus 2. Now I'm going to square both sides of this, and I end up with y prime squared equals x squared times x squared plus 2. And when I distribute that x squared, I get x to the 4th plus 2x squared. Notice I just distributed that x squared across there. Well, this is what I'm going to plug in place of the y square right here. So now I'm ready to set up my integral. So for the surface area, I'm going to get 2 pi times the integral from 0 to the square root of 2 of my radius we said was x times the square root of 1 plus x to the 4th plus 2x squared dx. Let's rearrange the order of these terms underneath the radical to be x to the 4th plus 2x squared plus 1. Does this factor? This is a perfect square of sums, isn't it? Do you remember your factor rules? If you had a plus b squared, that would FOIL out into a squared plus 2ab plus b squared. Well, if a is x squared and b is 1, this will be what I get, won't it? So that means that I can rewrite that radicand as x squared plus 1 quantity squared. So now we notice that the radical will cancel out with the square. The square and the square root will cancel out. And that's going to leave us with 2 pi times the integral from 0 to the square root of 2 of x times x squared plus 1 dx. I can continue to simplify the integrand by distributing this x. And that's going to give us, I'm going to move it over here, that's going to give us 2 pi times the integral from 0 to the square root of 2 of x to the 3rd plus x dx. And when we integrate that, what do we get? Add 1 to the exponent, that makes that x to the 4th. So this is a 1/4 x to the 4th plus 1/2 x squared, evaluated from 0 to the square root of 2. So now we can plug in our bounds. The square root of 2 is the same thing as 2 to the 1/2, isn't it? I'm writing it like that because it's easier to see what the exponents are going to simplify into by raising a power to a power. So this is 2 to the 1/2 squared. So this is what I get for my upper bound minus, and then you plug in a 0 for your lower bound and you get 0 plus 0. So we're ready to clean this up. That's going to give us 2 pi times 2 to the 1/2 raised to the 4th is 2 to the, when you raise a power to a power, you multiply the exponent. So that's 2 squared. 2 squared is 4, and 4 times 1/4 is 1. 2 to the 1/2 squared is just 2, and 2 times a half is 1. So this is 2 pi times 1 plus 1 is 2. 2 times 2 pi is 4 pi. That wraps up section 6.4.